This video is about ionization energy. So ionization energy is a very important property that we can measure about atoms. And the idea is that we're going to take an atom in the gas phase, and so I've represented that here in this equation by this letter A right here. So letter A just represents some atom, and it's a gas phase atom. And the idea is that we're going to add some energy to this atom, and we could do that in a couple of different ways. We could use light, so we could use photons as the source of energy. We could also use another high energy, fast moving particle, like an electron, and shoot electrons like bullets at this atom. And if we put in enough energy will go in and rip out one of the electrons on the atom and produce an ion, like this one right here, A+. So we've made an ion, and then we've removed this electron, and we imagine that that electron is now very far away from the atom from which it has been ionized. So we've made an ion, a cation in this case, so that's why this is called ionization energy, the energy to remove one electron. Sometimes we will call this IE sub 1, or the first ionization energy, because it's the energy to remove the first electron. You might imagine that we could put in more energy to Ag plus gas, add in some energy, and we could pull off the second electrons. Then we'd end up with Ag2 plus, still in the gas phase, and another electron. The amount of energy that it would take to do that would be IE2. And it is always the case that it gets harder and harder to pull an electron off an atom because you're pulling it away from something that already has a positive charge. And we know that there's a force, a strong force between positively charged things and negatively charged things. So it will always be the case that the second ionization energy is greater than the first ionization energy. And as you might imagine, we could have a third ionization energy and a fourth ionization energy, and so on until we have removed all the electrons that an atom has. Let's look at an example. Let's look at helium. So helium here in the gas phase, we're going to add some energy. We're going to make an ion. So what ion are we going to make? Well, we're going to make helium plus. Now helium only has 2 electrons, so we've removed one of the 2 electrons. And so it's going to take a certain amount of energy to do that, and we can measure what that energy is. Let's look at this in a little bit of a diagram. So I'm going to draw a little circle here for the nucleus and write +2. Now the atomic number for helium is 2. That means it has 2 protons in the nucleus. Each proton has a +1 charge, so that makes the nucleus, this little circle that I've drawn here, +2. So now we're going to imagine that we have a little ring around this atom, so a little orbit into which electrons could go. So that is supposed to be a circle, but you get the idea. And electrons will be red. So we're going to imagine that we have our 2 red electrons here on this orbit. So there's an electron, electron number 1. Here's electron number 2. So we're going to put in some energy, and we want to try to remove one of those electrons. So we're going to try to lasso one of those guys and take it off of the atom by putting in some energy. So what's going to determine how much energy it takes to remove this electron? Well, this electron is being attracted to the other particles in the atom, so to the nucleus, for example. And so how strong this electron is pulled to that nucleus depends on 2 things. So the force depends on 2 things. One, it depends on the charge that the electron feels. And that charge will be due primarily to the nucleus, but perhaps also to other electrons that are in the atom. The second thing that force depends on is the distance from the charge, the distance from the nucleus. I'll abbreviate that nuke. So the further we are away from the nucleus, the less force there's going to be, and the less energy we're going to have to put in. The bigger this positive charge, the stronger a force we're going to feel, the stronger a pull we're going to feel towards the nucleus, and the higher the ionization energy is going to be. So from our little simple pictures of what the electrons might be doing in an atom, we can sort of think about how the ionization energy might be affected by these 2 factors, charge and distance. So now let's look at some experimental data. So here are the measured values of the ionization energy, the first ionization energy, in units of kilojoules per mole right here for many of the atoms on the periodic table. So atomic number is on the x-axis here, so we're increasing the atomic number, adding 1 proton each step. So we've labeled some of the atoms, some of the elements here on this group. And so you'll notice that there's some interesting kinds of patterns that emerge. First off, it sort of has this general sawtooth shape, right? It goes up and then down and up and down and up and down, kind of like a saw might do, a sawtooth might do on a saw. The other thing that we kind of notice is that every time, if you're thinking about the periodic table, every time we go and start a new row on the periodic table, the ionization energy starts low and then seems to climb upwards, generally speaking. So it starts low, climbs up. Then we go to a new row of the periodic table. It starts low and generally climbs up. Now, of course, there are a few blips, and there's some areas where it seems to be a little bit flat, right? So there are a few blips. There's some areas where it appears to be flat. But generally speaking, there's a gradual increase as we go across a row of a periodic table. We also notice that, for example, if we compare some elements that are all in the same group of the periodic table, remember the groups are the columns of the periodic table. So like helium, neon, argon, krypton, xenon, and radon are all noble gases, and they're in that group 8 at the far right of the periodic table. So if we look at those ionization energies, we see that they all decrease going down a group. We would notice the same trend with fluorine, chlorine, bromine, and iodine, that in general the ionization energy seems to decrease as we go down. Let's put that in perspective with a kind of bar graph. So here's a bar graph showing that same data, although we've left out all those elements in the middle where it was relatively flat. So we've left out all the transition elements and the lanthanides and the actinides, so in this area. But you see that there's a clear pattern here, although there are some blips, but generally speaking, ionization energies are low over here in this corner of the periodic table. So this is low ionization energy. And we move up to this upper corner where helium is. That's where the highest ionization energies are. So that's going to be the highest ionization energy. So if we kind of will remember that pattern, that as you go generally across a row of the periodic table, ionization energy increases, and as you go up a column of the periodic table, ionization energy also increases. So if you'll kind of memorize that pattern, we'll be able to make predictions about how strongly any particular atom of an element will hold on to its electrons. So ionization energy is important because it tells us how strong an atom holds on to its electrons. So now our task is to figure out, well, can we explain this trend? So do we have a model of an atom that will explain this trend? So why is it that helium has the highest ionization energy? Why is it that ionization energy is over here if these metals are so low? So we need to come up with a model to explain these experimental observations. And that's what we're going to be doing in class and in the textbook reading.